Hello students, welcome to today's video. In this video we are going to discuss about the electric flux. Our main objective is to arrive at the Gauss law, which we have written here. We have to arrive at the Gauss law. Before going to Gauss law, we will have to know a quantity. We will have to study a quantity which is called the electric flux. Now, what is electric flux? This electric flux is denoted by the letter phi. Okay, here phi is the symbol for electric flux, and we have written here E since we have considered the electric flux. Therefore, we have written the subscript E. If it were a magnetic flux, then we would have written the letter B. Okay, that you will come to know in the magnetism chapters. Here, what is electric flux? It is just a measure of the flow of electric field through any given area. So we have to consider a given area. Here I have considered a given area. This is a diagram for electric flux. Here I have considered a certain area or certain area element. For this area element, what is the electric flux? Now it is a measure of the flow of electric field through any given area. That means what amount of electric field is flowing through this area. How much amount of electric field is flowing through this area. That is known as the electric flux, or it is a measure of the electric flux. In this diagram, what would be the value of electric field? See here, the electric flux is a quantity which is proportional to the number of electric field lines passing perpendicular to a surface. So we have considered here a surface, and how the electric field lines would be here. Here the electric field lines would be perpendicular to the surface. Okay, so this was the surface, and I have considered the electric field lines which are perpendicular to the surface. So these are the electric field lines for this diagram. So what would be the value of electric field for this diagram? See, what would be the value of electric flux for this diagram actually? So see, we have come to know that the electric flux is proportional to the number of electric field lines passing perpendicular to the surface. So these are the lines which are perpendicular to the surface. Now the value of electric flux is proportional to the number of electric field lines. So how many lines are passing through this surface? We have got 1, 2, 3, 4, 5. So 5 lines are passing through this given surface which are perpendicular to the surface. So the value of electric flux would be 5 in this case. Okay. So finally we have to arrive at the Gauss law. Before going to Gauss law, we will have to first study what an area element is, or what is the direction of the area element vector. Now you will come to know that the area element is nothing but it is a surface, and the direction of area element vector is perpendicular. How? Let us first consider a two-dimensional surface. Okay, we have considered here a square, which already you know is a two-dimensional surface. I have represented this square along the xy plane. Okay, I have drawn here the three rectangular coordinate or the rectangular coordinate system. So here I have drawn the x coordinate, here y, and this is the z direction. Right? This is the rectangular coordinate system, and in this rectangular coordinate system I have represented a square of side A in the xy plane. Now what would be the area of this square? The square is PQRS. What would be the area of the square PQRS? The area would be, as you already know, it's side into side, or we may write side square. So this would be A square. Now is this area a scalar quantity or a vector quantity? You all would be thinking that this is a scalar quantity since we just multiply the sides, so it's a scalar quantity. But see, I have represented this square in the xy plane. Okay, I have represented this in the rectangular coordinate system. So this length, which is the PQ length can be taken to be a vector, right, which is along the x direction. Similarly, we can also take the QR length to be a vector quantity which is along the y direction. Right? So what we have done here is we have just multiplied two vectors. That means this is a vector and this is also a vector. Okay, PQ is a vector and QR is also a vector. If we multiply these two vectors, then what is the angle between them? The angle between them is 90 degree. Okay, the angle between PQ and QR is 90 degree. So if you multiply these two vectors, what we are doing, we are just taking the cross product, right? So what we are doing is we are taking the cross product of PQ and QR. This is a cross. So if we take the cross product of two vectors, then what would be the resultant? The resultant is also a vector quantity. That means in this concept, the area is a vector quantity since we are taking cross product of two vectors, right? See, what would be the value of the cross product now? The value of the cross product would be PQ. What is the value of PQ? A, and QR is A. So AA, as you know that the resultant of a cross product of two vectors is vector A into vector B into sine of the angle between the two vectors. So here I have done PQ into QR sine 90 degree. The angle between them was 90 degree. Therefore I have written here 90 degree. So what is the resultant? We get the resultant to be A square. So is this A square a scalar quantity? No, it is a vector quantity. Okay. Now what is the direction of this resultant vector, this area vector? Okay, we have considered the element to be PQRS, and what is the direction of that element? What is the direction of that resultant area vector, right? So as you know that if we take cross product of two vectors, then the resultant vector is always perpendicular to the direction, perpendicular to the plane containing the two vectors. Okay, you have already read it in class 11. So what would be the direction of the area vector? That will be the direction of the resultant vector, which is the area vector, is of a cross product of two vectors is always perpendicular to the plane containing the two vectors. Okay, so what we have got here is the direction of the resultant vector, area vector of this plane surface which lie on the xy plane. For that plane surface, the resultant vector is along the perpendicular direction. That means according to this figure, the direction of the area vector would be along the z direction. It may be either positive z direction or the negative z direction, right? So for two-dimensional objects, the direction of the area vector would be along either the positive z direction or the negative z direction. The direction is taken in both ways. Okay, next we will have to study the direction of the area vector for three-dimensional objects. Let us now check the direction of area vector for three-dimensional objects. We have already done two-dimensional objects. So for three-dimensional objects, what would be the direction of the area vector? See, in this diagram, I have taken a three-dimensional volume. Okay, this is just a cube. So for this cube, what would be the direction of the area vectors? So in order to determine the area vectors, we will have to first consider the surfaces. So for this surface, what would be the direction of the area vector? As we know that for this surface, if we calculate the area, we will have to multiply this side with this side. Okay, so these two are vectors. What would be the direction of resultant of those two vectors? That will be perpendicular to this surface. Okay, the direction of area vector would be along this direction, which is perpendicular to this surface. Similarly, for this surface, what would be the direction of area vector? That would be perpendicular to this surface. For the third surface, for this surface, the direction of the area vector will be perpendicular to this surface. Okay, so similarly for all the faces, we can calculate the direction of we can determine the direction of the area vector, right? What would be the case for a three-dimensional sphere? This is a sphere, so what would be the direction of the area vector for a three-dimensional sphere? See, if we draw a perpendicular at any point on the sphere, on the surface of the sphere, then if we draw a perpendicular here, then how would be the perpendicular? It will be a line passing through the midpoint. Okay, so similarly at every point, if we draw perpendiculars, then those perpendiculars will be perpendicular to the surface, to the small element at this point. Okay, similarly if you consider a small area element at this point, then that perpendicular would be perpendicular to this surface, right? So for every point, if you consider every point on the sphere, if you consider small area elements, then these area vectors will be perpendicular to those area elements, and the direction of this perpendiculars should be such that these perpendiculars pass through the midpoint of the sphere. Okay, so this is the direction for the area vectors. These are the direction of area vectors for a sphere, which is a three-dimensional object. Now, what was phi e? That was the electric flux, and this it is proportional to the number of electric field lines passing perpendicular to a surface. Now, here we have considered a surface here whose area is A. Okay, the electric field here in which the surface is placed is E. The electric field is E, right? So what would be the value of electric flux for this surface, or how it will depend, how the electric flux will depend on these two factors? See, first of all, if we increase the electric field, that means what? If we increase the electric field, that means the density of electric field lines will increase. Okay, so if the density of electric field lines will increase, and if the area of the surface is constant, then more number of lines of force or more number of electric field lines can pass through this surface perpendicularly, right? So what will happen if we increase the electric field, then the number of electric field lines passing through this area will increase. So we will get more electric flux. Similarly, if we increase the area, of this surface, then what? This area can accommodate more number of lines of force or more number of electric field lines. That means if we increase the area, the electric flux will also increase. So what we can see here is that the electric flux phi E depends on the electric field as well as the area. So what we have seen up till now is that the electric flux phi E depends on the electric field as well as the area. Okay, so how does it depend on the electric field as well as the area? Let's see in this diagram. Here we have placed a surface. Okay, the angle between the okay, first of all, let's see the area vector of the surface. Now, in which direction will this will the area vector of the surface be? Okay, the area vector will be perpendicular to the surface, right? So the direction of area vector will be along this direction. This is the area vector for this surface. Now see, the electric field is along this direction, and what is the angle between the electric field and the area vector? This is theta. Okay, I have written here the angle between the area vector and the electric field vector is theta. So this angle is theta. Now the electric field can be represented or can be resolved into two components. First, one vertical component, that is E sin theta, and another a horizontal component, which is the E cos theta. Okay, so here I have resolved the electric field into two components, which is the E sin theta along the vertical direction and E cos theta along the horizontal direction. Okay, now see, which component of electric field shall we choose? We will have to choose the vertical, we will have to choose the component which is perpendicular to the surface, right? So which component is perpendicular to the surface? We will see that only this component of the electric field is perpendicular to the surface, because in electric flux we used to consider only the lines of force which are perpendicular to the surface, not those which are parallel to the surface, right? So in this case, what will be the electric field which is perpendicular to the surface? That will be E cos theta. So here we don't consider E sin theta component, we consider only the E cos theta component. So what we can write is phi E depends on the E cos theta component and the area, right? So we can write this as E A cos of theta. This is the electric flux for this surface. What we have finally got, we got the electric flux phi E to be E A cos of theta. So what is this? E A cos theta. This is nothing but the dot product of E and A, right? So we have written here E dot A, and this is the electric flux. So finally what we have got is a scalar quantity. Electric flux is a scalar quantity, which is the dot product of the electric field as well as the area A. Okay, now how this is a scalar quantity? As we know that if we take dot product of two vectors, then the resultant is always a scalar quantity. Therefore we have got here the electric flux to be a scalar quantity. What is the unit of electric flux? So we have taken the formula E dot A. In place of E we have written here F by Q naught, and A will be there, right? For force we have the unit of force is Newton, and the unit of charge is coulomb. So we have written here Newton by coulomb. For area we have the unit meter square, so this becomes Newton per coulomb meter square. This is the unit of electric flux. Similarly, what would be the dimension for electric flux? The dimension for Newton, or we have MLT minus 2, which is a force. We have MLT minus 2. For coulomb we have AT, and here we have coulomb inverse. So this would become A inverse T inverse. For meter square we have L square. So finally the dimension of electric flux becomes M L cube T minus 3 A minus 1. This is the dimension for electric flux. So far we have calculated the electric flux linked with a large area. In this part we are going to calculate the electric flux linked with small area ds. Okay, for this we consider a surface area here. This surface is S, and in that surface area we consider a small area element ds. Okay, the surface is like this, and in this surface we have just considered a small area element ds, right? So what would be the direction of the area vector? The area vector will be perpendicular to the surface. So if this is the area, then we get the area vector to be perpendicular to this surface in this way. So what I have drawn here is the area vector along this direction, which is perpendicular to the surface. Next, if the electric field is along this direction, then what is the angle between the area vector and the electric field? That is theta. Okay, I have taken the angle between the area vector and the electric field vector to be theta. So now we can resolve the electric field into two components, one vertical component which is the E sin theta, and one horizontal component which is E cos theta. Since this is the angle theta, therefore we have this component to be E cos theta and the component which is parallel to the surface to be E sin theta. And in the calculation of electric flux, which component do we consider? We consider only the cos theta component, right? So what we have to consider here is only the E cos theta component of the electric field. So how do we calculate the electric flux? We have written here d phi E. That means this is the small electric flux linked with the small area ds. So this the value of electric field component along this direction is E cos theta, and what was the area vector? That was ds. The area vector is ds. So what we get, d phi A to be E cos theta into ds. This can be rearranged as E ds cos theta. Now what do we get here? E ds cos theta. That is the dot product of E and ds. So we have written here d phi E as the dot product of E and ds. Right? So this is the value of small electric flux linked with a small area ds. Now if we have to calculate the total electric flux for this whole surface, then what do we have to do? You already know that this is the small electric flux linked with the small surface. So for the whole surface, if we are required to calculate the total electric field or total electric flux, then what do? We just integrate this value. Okay, so similarly we have done the same thing here. The total electric flux linked with the whole surface is phi E. Okay, I have integrated this over the whole surface, so I have taken a closed surface integral. This is known as closed surface integral, since we are considering the surface to be a closed surface. So if we integrate d phi E, then what we will get? We will get the integration of E dot ds. If you integrate this value, then you will get the total electric flux linked with this surface. Here we consider two special cases. The first case is if E is perpendicular to the surface. So this is the surface ds. If E is perpendicular to the surface, then in what direction will the vector E lie? The vector lies in this direction. Since this is the surface and E vector is perpendicular to the surface, therefore we get E along this direction. And we also know that the direction of area vector is perpendicular to the surface. Therefore the area vector will also lie in the same direction. So what we get here is the electric field vector E and the area vector A are parallel to each other. So what would be the angle between them? That will be equal to 0 degree. So here theta becomes 0 degree. For this case, what would be the value of small electric flux linked with this surface? That would be equal to E ds cos theta. Here theta is 0 degree, so we get E ds. this so what we get is E d phi E, that is the electric flux will be maximum when the electric field is perpendicular to the surface. Okay, the electric field must be perpendicular to the surface as well as parallel to the area vector. Only then the electric flux will be maximum. What will be the case if the electric field vector is parallel to the surface? If the electric field vector is parallel to the surface, that means we will get the electric field vector along this direction. Okay, if this is the direction of electric field vector, the area vector lies perpendicular to the surface. So what will be the angle between E and A? That would be 90 degree, right? So in this case, what will be the value of d phi A, that is the electric flux, small electric flux linked with the small surface ds, will be E ds cos of 90 degree, since the angle between E and A is 90 degree here. So ultimately what we get the electric flux to be 0, which is minimum. Okay, so what we have studied up till here is the electric flux, and in our next video we are going to study Gauss law using this electric flux. Okay, thank you.